In this example problem, we have a dragster reaching a top speed of 60 meters per second before we apply the brakes and bring the car to a stop at a rate of 8 meters per second squared. The question asks, how long will it take the car to come to a complete stop? Well, let's start with drawing a picture. All right, we have a car. Not the prettiest car. And we know that it has already sped up. Now, they don't give you any time frame that it took to get up to 60 meters per second. So we actually don't know how it accelerates to get up to speed. All we do know is at this point, the brakes are applied. So this is really when the problem starts. And so we're at some location. Right, we're going to draw our picture here. And this car is located somewhere. It already has velocity. So we're going to draw a velocity vector. This is V initial. And we know it is 60 meters per second. That's given in the problem. Right, this car is slowing down. Right. But as it slows down, it's still covering some ground. So later it's going to be located somewhere else, right? And when it gets to this point, all right, we'll call that our final position. This would be our initial position. What do we know about this car? Well, it's come to a complete stop. So at this point, we know that the final velocity is 0 meters per second. Well, if we're going to be slowing down, then something must be pushing us, right? That would be the brakes in this case, or really the friction with the road when you apply those brakes. But in order to subtract away velocity, that push to slow us down is going to be to the left. And that's going to be our acceleration. Now, the value of that acceleration is 8 meters per second. So how long that arrow is 8 meters per second. But we're going to make sure that we put in a negative value in our data table. And I'll put negative here just to be very clear. That's what the leftward arrow means. Don't forget that we're calling right positive as our general convention, right? So this is a positive 60 meters per second. Last thing we don't have, which is really what the problem is asking for, is what is the time it takes to stop, right? So it's going to take time for the brakes to subtract velocity away from that car. So here's a nice little picture. You kind of get a sense of what's going on. I'm also going to draw a position time and velocity time graph for this problem. I think it's helpful to be able to visualize how the motion of an object relates to these graphs. So I'm going to put them right on top of each other. So the times are happening, the motion as far as the position and the velocity. It's a little easier. You can see how they relate when they're right on top. We're calling that the positive direction. And let's walk through what this car is doing. It is starting somewhere. And we don't know where that is. Well, let's decide to start it at 0, right? And if it's moving as it slows down later, it will be located further away from 0, right? So all we know here in my table is they haven't told you where it's located. So let's just call that 0 meters. And then after the braking period, it'll be located somewhere. The problem doesn't ask for it, but we could get that later. Well, all we know are these locations. But what do we know about the speed? Well, it has velocity at the start. And it has velocity to the right. So when I think velocity on a position time, I'm thinking slope. So I'm going to draw a nice steep slope at the start. This car is not going to be going any faster than 60, so that's going to be my steepest slope. And that means that on my velocity time graph, I can plot a steep slope or a high velocity data point up here. And again, I won't be going any higher than that. Well, what happens at the end? Well, this car is losing velocity. Velocity is going down. Therefore, the slope is decreasing on the position time graph all the way down until the car stops. And that is a slope of 0 because the car is not moving, and I can plot a value of 0 on the velocity time graph. All right, so hopefully you start to see that we get this shape on the position time graph where we're going to get a curve. Right, that's a parabola, downward facing parabola. On the velocity time graph, we're losing that at a constant rate. Right, so we get this downward slope. And what is the slope of that? Well, the slope on this graph, if we recall on a velocity time graph, is the acceleration, which is going to be negative 8 meters per second squared. And that parabola, we would see that changing slope. The slope is decreasing by 8 meters per second every second. All right, so where do we go next? Well, a good strategy is to organize the variables we have. We really have two equations that model motion. We have a position function, which is really the parabola. It's a t squared function, 1/2 at squared, plus the initial velocity times time, plus the initial position. So that's our position function. Let's just call that equation 1. We also have an equation for the velocity time graph, and that's a line which defines the final velocity as a times t plus v initial. So these are our two equations that will define where it's located, equation 1, and how fast and what direction its velocity in equation 2, both of which have time in there. So we're going to look at this problem and see if we can figure out what the time is going to be to stop. And so I'm going to write out the variables that I have. I have an a, I have a t, I have two velocities, I have an initial position, and I have a final position. All right, these are the possible variables. This is my ATVX table, right, where ATV and X are the variables given. All right, so we know the acceleration. It is slowing down. It is a negative acceleration. The arrow I drew points to the left to push on that car and slow it down. We don't know the time. I'm going to leave this blank. And since they want that answer, this how long, that's a time, I'm going to put a star next to that because I know that I want that as an answer. My initial velocity is a rightward arrow, so I'm going to put a plus 60 meters per second. Always a good idea to put positive or negative with our velocities. And if it stops, it's going to be going 0 meters per second. We decided to start it at a position of 0 meters, and it's going to finish somewhere. This problem does not ask where it finishes, but we can find that out. All right, so where do we go from here? Well, let's look at our equations. A good strategy now is to identify from our table what do we have. Everything I don't have, I'm going to put a question mark over it. So we don't know where it's going to be located at the end. We also don't know the various times. All right, so I'm going to put a little question mark over all the t values. And then things I do have, I'm going to put a dot or a star. We have the acceleration. I'm going to put a little dot over the a, and it's in both equations. We have the initial velocity. I'll put that here and here. And we have our final velocity of 0. So I'll put that there. And we have our initial position. All right, so at the end of this process, I have a dot over every unknown variable in these equations. And I'm asking myself, well, does one of these equations have only one missing variable? Well, sure enough, equation 2 has everything except t. So if I want to find time, I can use equation 2 to get the time. And so the equation 2 says that v final is equal to a times t plus v initial. And now I'm just going to substitute in my values. V final is 0 meters per second. A is negative 8 meters per second squared. My time is unknown. I'll leave it there. Plus my velocity when I start of 60 meters per second. And now it's an algebra problem. Right? I have 8t plus 60. I put the units in there because I want to show you how that they will match up. But in the future, as long as all of these variables are meters and seconds, you're going to be just fine, and the answer will spit out the right units of whatever you have in the table. All right, so to get t by itself, I'm going to add 8 meters per second squared t, right? That's really adding 8t. So I'm going to add that here. Again, I'm just keeping the units in there, and that's going to get rid of that. And now I have 8 meters per second squared times time is equal to 60 meters per second. And if I want to solve for t, I'm going to divide both sides by 8 meters per second squared. And we see that that cancels. Now look at my units, right? I'm going to get meters canceling. And I got seconds divided by 1 over seconds squared. And that's actually going to cancel here, and it's going to bump a seconds in the numerator, right? And if I want time as an answer, seconds is a reasonable unit for time. Let's do a little calculation. What's 60 divided by 8? And sure enough, I get 7.5 seconds. So the time to slow down is 7.5 seconds. That is going to be my answer for how long it'll stop. Right, so after 1 second, this car has lost 7.5 seconds. It's now going 52.5 seconds meters per second. Another second later, after 2 seconds, it's now going only 45. Then after 3 seconds, 37.5. Then 30 after 4, and so on and so forth until it gets all the way down to 0. All right, so that's how acceleration works. In this case, we're accelerating to the left for an object that's moving to the right. So pretty good process here. There are certainly more than one way to do this. Some of you guys might realize, hey, we have a change in velocity and we have a time. This equation may look familiar to you, right? If I took this equation, this is really the definition of acceleration, the change in velocity over time, right? And I can solve that equation to get t just like I did before. And I would end up with t is equal to the change in velocity, v final minus v initial, all over the acceleration. Sure enough, isn't that what we did here once we did this algebra? Right, so you can solve this. These are all the same equation to get to where we need to go. But I really think drawing a good picture, understanding position time graphs, but ultimately being able to identify what's given in the problem, this ATVX table, is critical to kind of figuring out the next steps in solving the problem. Best of luck. Here's all the work, and good luck on this problem.